A very good morning to all my dear students. Welcome back to the third class of the online session 2020-2021. So again we are back with the chapter Magnetic Effects of Electric Current. So I hope the previous day in the last class, whatever topics were done, your Fleming's left-hand rule, all these things you have already studied about it, okay? And again, if you have any problem, you can mail it to us. Okay, which is there, the mail ID is already given in the portal. So today I start with the next topic of the chapter, Magnetic Effects of Electric Current. The next topic is electric motor. I hope all of you can see the diagram that I have drawn. The diagram of electric motor. You are going to get this diagram in your NCERT book. Alright? So what you need to do is you have to understand the working of the electric motor. And before that, I would like to tell you what is an electric motor. An electric motor is a rotating device which converts electrical energy into mechanical energy. I hope I am clear. What is an electric motor? An electric motor is a rotating device which converts electrical energy to mechanical energy. What is the principle of this electric motor? What is the principle of this electric motor? Very important question. The principle is that when a rectangular coil, you can see the rectangular coil I have drawn, A, B, C, D. This is a rectangular coil is placed in a magnetic field and current is passed through this coil will experience a force, okay, which will rotate it continuously. So this is the principle of electric motor. Okay, very important. So what is an electric motor and what is the principle of an electric motor? There are various components which uses electric motor inside them. Like we have the electric fans, we have washing machines, we have mixers. So many kinds of components are there which uses electric motor. Now we are going to study this diagram first and then we are going to proceed with the working of the electric motor. So look at the diagram, all of you. I have written North Pole, South Pole. So these are the two, the poles of the magnet. And this is a rectangular coil A, B, C, D. This is a rectangular coil which is attached to the brushes. X and Y are called the brushes. I hope you can see. I have written it with blue ink. This cylindrical thing that you are seeing, where the brushes and the split rings, there are two rings which are split. P, Q are known as split rings. Okay, X and Y are called brushes. These brushes are attached to the split rings. And P and Q are the split ring. This is the axle on which the split rings are actually mounted. Okay. So the inner surface of the split rings are insulated and it is attached with the axle. And X and Y are the brushes which are the conducting brushes, means they can conduct current. We have battery, we have a switch. Okay, and we can see clearly from the diagram that this rectangular coil is placed in a magnetic field. Okay, and we know from Fleming's left-hand rule that if the magnetic field and your this current, they all are mutually perpendicular, the direction is mutually perpendicular to each other, the force exerted will be maximum. Okay. So alright, so you can see this rectangular structure, the coil A, B, C, D. Another thing, you can see that when current is switched on, when the circuit is switched on, current will flow from the positive terminal to the negative terminal of this whole structure. So when it flows like this, current is flowing from A to B, then C to D. You can see the two arrows I have drawn with blue color. A to B, then C to D, and then through the brush Y and back to the the battery. So this is what is happening. Okay, so the working of this. So current is flowing from the coil A to B. Okay, then from C to D, this is what I have told you. So this coil, rectangular coil, is going to experience some kind of force on it, which you can find out with the help of Fleming's left hand rule. And when you apply Fleming's left hand rule, you will find that this particular portion of the coil AB will be moved downwards and CD will come up. So AB goes down, CD goes up. So in an anti-clockwise direction, it will rotate. Okay, when half rotation is completed, this split ring P is going to touch the brush Y, and the split ring Q is going to touch the brush X. And again, current will flow through the brushes X and Y because they are conducting brushes. Okay, so what will happen? The direction of the current will be reversed. This time, current will flow from D to C and then B to A. Once again, I am repeating here, after half rotation, when AB and CD, when current is flowing from A to B, from C to D, so there will be a rotation in the coil in the anti-clockwise direction. Now what you can do is, what will happen is, this brush is X and Y, brush Y will come in contact with the split ring P, and brush X will come in contact with the split ring Q. As a result, the direction of the current will be reversed. And when the direction of the current will be reversed, this coil, this time, the force that will be exerted is CD will go in the downward direction and AB will move in the upward direction. You can find out the force, the direction of the force again from Fleming's left hand rule. Alright. So this is what will happen, and that means after every half rotation, this is going to, the direction of the current gets reversed. Who reverses the direction of the current here? Here the split rings P and Q actually reverses the direction of current, and here the device which reverses the direction of current is known as a commutator. In this case, in case of the electric motor, it is actually the split rings P and Q who are acting as commutators, and commutators, they will actually reverse the direction of the current. So this is what happens in case of an electric motor. So since the current is constantly getting reversed, the direction is getting reversed, this particular rectangular coil will constantly, it will keep on rotating. Okay, and as we know from the definition that an electric motor is actually a device, it's a rotating device which converts electrical energy into mechanical energy used in various components like mixers, electric fans, washing machines and so on. This is the working of an electric motor, and this diagram is very important for your exam. So you have to remember this thing. What is a commutator? What is an electric motor? What is the principle of an electric motor? What are these brushes? Okay, the rectangular coils, how are they working? How they are constantly rotating. They are constantly rotating because the direction of the current is getting reversed after every half rotation. Alright, so this is about your electric motor. Okay, so after the electric motor, moving on with the next, important thing, topic related to the electric motor. What about the commercial motors? What do they use? Instead of a permanent magnet, a commercial motor uses an electromagnet. I hope you know what is an electromagnet. It's actually a temporary magnet, and this electromagnet will work like a magnet only when current is passed through it. Okay, so instead of using permanent magnets, they use electromagnet. Large number of turns of the conducting wire. If large number of turns are used, the magnetic field also increases. Okay, so in the conducting wire carrying current, large number of turns are used, and another thing is a soft iron core is also used. It is passed through the coil. a soft iron core is passed through the coil. So remember, for a commercial motor, these are the three things they use. They actually use an electromagnet instead of a permanent magnet. They use large number of turns of the conducting wire carrying current, and a soft iron core is passed through the coil, or it is wound. A coil is wound around a soft iron core. So these are the three things you have to keep in mind, that for a commercial motor, these are the things that they actually use. Okay, so moving on with the next topic of the chapter, electromagnetic induction. We all know that when a current carrying conductor is placed in a magnetic field, okay, and the direction of the current is perpendicular to the direction of the magnetic field, the conductor is going to experience a force, and this force is enough to move the conductor. So let us imagine a situation where the conductor moves in a magnetic field. Okay, so this experiment was first done by an English physicist, Michael Faraday. I think many of you have heard his name, Michael Faraday. So let us see, what did he observe? He had observed that when, he had taken a coil of wire, okay, attached it with a galvanometer, and there was a bar magnet he had taken. And when this bar magnet, the north pole of the magnet, when this bar magnet was pushed inside the coil carrying current, this galvanometer was showing a deflection. This deflection was towards the right. So when there was a motion of the magnet, there the galvanometer was showing deflection. Now what is a galvanometer? It's a device which can detect current. Mind it, there is difference between ammeter and galvanometer. Ammeter will measure the current and galvanometer will detect whether current is present in the circuit or not. Okay, that means what was his observation? When this magnet was moved, when there was motion, that time there was a current which was produced. So if you move a magnet within the coil, what was happening? A current was induced in the coil. This is induced current. So we can make, you can create, you can, this current you can, if this magnetic, if this magnet is moved, if there is a motion, then current can be induced in that particular coil. So this was his observation. Well, in the first case, the galvanometer is showing deflection towards the right because this particular movement of the, the magnet is towards the left. He was pushing it. Now, when he pulls the magnet away from the coil, the galvanometer was showing a deflection towards the left. That means, again there was an induced current, but in this case, since, the direction, the movement is in the opposite direction, the current, the deflection in the galvanometer is also in the opposite direction. That means you can change or reverse the direction of the current just by reversing the direction of the magnetic field. Okay, if you reverse the direction of the magnetic field, you can reverse the direction of the induced current. This was the first observation made by the English physicist known as Michael Faraday. Alright, so we will move on with the next, based on this observation. Okay, there are few things to be noted, that there are two things you can see. One is the coil, another is the magnet. Out of these two things, you can keep one particular object stationary. In this case, we have kept the coil stationary and the magnet, there is a movement in the magnet. Okay, so the movement in the magnet is showing actually deflection in the galvanometer. That means a current is induced in the galvanometer. Alright. Now, instead of this, we can keep the magnet fixed and we can move the coil also. You will observe the same thing. So, out of both the things, one particular object can be kept stationary, but there should be movement in the other object. Either the coil, there can be a movement in the coil, or there can be a movement in the magnet. Okay, if you find that there is no movement in both the things, the magnet also and the coil also. If there is no motion, this galvanometer will show zero deflection like this. There will be no deflection in the pointer of the galvanometer, which shows that there is no induced current if there is no movement in the magnet of the coil. When there is no change in the magnetic field, what will happen? There will be no induced current will be produced. So the galvanometer will show no deflection. Okay. So this was the experiment which was done by Michael Faraday. Moving on with the next activity. Let us see what exactly happens. Okay, so here is the activity that I was talking about. Okay, the activity is that you can see there is a cylindrical, this is a non-conducting roll. Mind it, a cylindrical non-conducting roll. And there are two coils, you can see coil 1 and coil 2. Coil 1 has got more number of wounds than or more number of turns than coil 2. So coil 1 is known as the primary coil. Coil 2 is known as secondary coil. You can see from the diagram that coil 1 or the primary coil is connected to the source of current through a battery, and coil 2 is just connected to a galvanometer. So there is no source of current in coil 2. What happens when current is passed through this coil? What will happen? The observation was seen that when you switch on the current, there was a momentary deflection in the galvanometer in coil 2. As soon as you switch on, there was some deflection in one side, and then immediately the pointer came back to 0. There was a deflection, immediately the pointer came back to 0 as soon as the current was switched on in the primary coil or coil 1. Okay, that means there will be no deflection if a steady current flows through coil 1 or the current is 0. Steady current flows through coil 1 or if current is 0, then there will be no deflection in the galvanometer of coil 2. So only if you start or stop, only if you change the current, then only this galvanometer will show some deflection. Alright. Now why is this happening? When current is passed through the coil, there is a magnetic field created by this conductor, we know. When current flows through a conductor, what happens? It behaves like a magnet. So there is a magnetic field around the conductor. So this coil 1 has magnetic field, and because of this, there is magnetic field in coil 2 also. As a result, there is an induced current which is being created or produced in coil 2, that is the secondary coil. There is an induced current in this coil 2. Got it? So this phenomena is known as electromagnetic induction. So what will we talk about? What can we say about electromagnetic induction? The process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. Once again I am repeating, the process by which a changing magnetic field in a conductor induces a current. So the induced current is actually in coil 2, because coil 2 is not connected to any source of current. Only coil 1 is connected to a source of current. So there is an induced current in coil 2 because of the magnetic field due to coil 1. Okay. So it induces a current in another conductor, and this process is known as electromagnetic induction. Got it? So in this electromagnetic induction, we have got a new term, that is induced current. Okay, in most of the cases, it is seen that the coil, if you move a coil in the magnetic field, an induced current is produced, and most of the cases this is used. The coil is moved. Now, how can you find out the direction of the induced current? So there is another rule, that is Fleming's right hand rule. You have studied about Fleming's left hand rule. You have studied about Maxwell's right hand thumb rule. This time it's a new rule when you have to find out the direction of induced current, that is Fleming's right hand rule. And Fleming's right hand rule is like this. If you hold your thumb, your forefinger and your middle finger at right angles mutually perpendicular to each other, such that this thumb is actually pointing towards the movement of the conductor. This thumb will depict the movement of the conductor, and this forefinger is actually the direction of the magnetic field. Your middle finger will show you the direction of induced current. So you can find out the direction of the induced current through Fleming's right hand rule. This is how you are going to place your right hand. Your thumb will show the movement of the conductor, your forefinger will point towards the direction of the magnetic field, and your middle finger will show you the direction of induced current. So you can try it along with me like this. So if they are mutually perpendicular to each other, you have to keep it like this. Got it? So this is your Fleming's right hand rule. So today we have studied about electric motor. Okay, we have studied about electromagnetic induction, how Faraday, he had observed this electromagnetic induction. We get the concept of induced current. That is, if a magnetic field is, changed by passing current, then if a magnetic field, is changed, if you move a coil or a magnet, what happens? It induces a current. You can produce a current, so that is your induced current. What is electromagnetic induction? And we have studied about Fleming's right hand rule. So there are some questions I have given you in the worksheet. Kindly solve the worksheet and you mail it to us. Okay? So thank you for today and have a good day.